Alright, this is Jack Jackson back again with the fourth part of our series of lectures on polynomial relations. And earlier we had talked in the first three videos about polynomial expressions and manipulating them, adding them, subtracting them, combining like terms, multiplying, dividing, that sort of thing, and factoring. And in this video we're going to start now talking about polynomial functions. So you have y equal to a polynomial. So polynomial functions can be put in the form p of x equals a sub n x to the n plus a sub n minus 1 times x to the n is minus 1, and so forth, all the way down to a1x plus finally a sub 0, where n is a natural number, and the a sub i's are real constants called coefficients. Of course, x is your input variable, p or y or f of x there is your output variable, so p is the output. And we're going to assume that this first one, a sub n, is not 0, but the others, a's, could be 0 if they want. So the a sub n times x to the n is called the leading term, and the a sub n is called the leading coefficient. And this polynomial is in decreasing order, and the n, the highest power, is the degree of the polynomial function. So we've already studied polynomial functions with low degree. Right? Degree 0 polynomials are just constant functions. There's not much to them. They're just horizontal lines. Degree 1 polynomials are linear functions, and we spent quite a bit of time doing linear functions forwards and backwards and every other way. So we really understood linear functions because they're very, very important. And just recently we've also done polynomial functions of degree 2, which are quadratic polynomial functions. Well, it turns out that we've also done power functions where it's y equals x to the n power for some different numbers n, and of course those are polynomials if n is a natural number. Well, all functions that are constant functions, degree 0 polynomials, are just vertical shifts of y equals 0. All linear functions are just transformations of y equals x, and all quadratic functions are just transformations of y equals x squared. So once we know what those things look like, we get our general functions. And let's review that a little bit with some Graphmatica here. So notice if I start with y equals 0, then if I change this to y equals 1, that's just a vertical shift. Or y equals negative 3.7, that's a vertical shift. So all constant functions are just vertical shifts of y equals 0. We can get all linear functions by transforming y equals x. So if we start there, we put a coefficient, say a 2 in front. Now we make it twice as far from the x-axis, so we stretched it vertically. And now if we add 9 to that, it shifts the whole thing up vertically. And so all functions can be thought of this way for linear functions. Again, we put our coefficient there, like negative 6x, and that could be not only a flip over the x-axis, but also a stretch. And then to that, we could say add negative 4, shift it down there. So all linear functions basically are just transformations of y equals x. Well, how about y equals x squared? Well, x squared, y equals x squared looks like this. If I put a coefficient in front here, like, let's say a half, okay, that's going to be a vertical compression. Half is close to the x-axis. What if I make another one? What if I make it to 1/8? So we've compressed it even more. Now let's suppose we take that one and replace x now by x minus, let's say, 10. That's going to shift it to the right 10. And then if I say maybe negative 5 at the end, subtract 5, that's going to move it down 5. And so it turns out, we found this by completing the square, that every polynomial function of degree 2, every quadratic function, can be written as this form. This is the vertex form of a quadratic, And so every quadratic is just a transformation of y equals x squared. So the thing you might think at this point is, hey, wait a minute, everything is maybe all polynomials are just transformations of simple power functions. Well, not true. We can get some cubics that look like that. So for example, 2 times x minus 4 cubed plus 5. That's going to be just like y equals x cubed, just shifted around, stretched perhaps, well, definitely stretched twice as much vertically, and then shifted to the right and up. Okay? But look what happens if I start adding some other terms here. Now, that graph is not just like a y equals x squared shifted around. It's got some of the same features that are very similar, but some key features are different. For example, this one has a maximum and a minimum. It goes up, down, up. So it's increasing part of the time, decreasing part of the time, then increasing again. Whereas those two cubes are either all increasing, or if, of course, if it has a negative coefficient, say negative 2x cubed, then it's going to be all decreasing. Like that. Typo there. So, it turns out that all polynomials are not just transformations of power functions, but they are kind of what I'll call well-behaved. So they do have some things in common. Their domain is always a set of all real numbers. Their graphs are one connected piece, so they're continuous. So there are no breaks, no holes, no horizontal or vertical asymptotes. Some of those things we've found in some other kinds of functions, like exponentials had some horizontal asymptotes. Logarithms had vertical asymptotes. There's a hole in the graph for a power function when the power was 0. There are breaks in the graph if you have power functions where the power is negative. Remember, all our powers here are positive, and they turn out to be just one connected piece. In fact, the domain is everything, so they go all the way from minus infinity to infinity, all one connected thing. They also are smooth. In calculus, we would call this differentiable. And what that means is there's no sharp corners or places where the graph goes vertical or almost vertical. So if you zoom in anywhere close, they look like a linear function. Let's see if I can demonstrate that just with a quadratic for that matter. Y equals x squared, just y equals x squared. If I take this, it doesn't look at all like a linear. But if I zoom in on part of it here, if I zoom in close enough, it looks pretty much already starting to look very much like a linear function. So if you zoom in close enough, it's going to look like a linear function. Even if I zoom in here close to this part, this doesn't look like linear yet. I have to zoom in quite a bit closer. But if I zoom in here very, very close, it's starting to look more and more like, just like the x-axis, like a horizontal line. So if I zoom in close enough, it looks like a linear function. We call this property local linearity, that if you go in close, it will be approximately like a linear function. Okay? And, well, differentiable functions, smooth functions in general look like that's true. So this is also true for exponentials and logarithms. But definitely polynomials have that characteristic. Now let's think about the end behavior. When I say end behavior, technically there are no ends. It goes all the way to, from minus infinity to infinity. But on the outside, let's see what happens to the graph. Now the thing to know here is, let's remember some things about power functions. Okay, and let's review a couple things. Here's y equals x squared. Let's do y equals x cubed. That was weird. There we go. I don't know what happened there. Y equals x to the fourth. Y equals x to the fifth. Okay. Well, of course, there's a big difference in the even and the odd, so let's remember that. The even power functions, the arrows point up on both sides. And in the odd power functions, the arrows point one up and one down. But let's just look at, let's zoom out a bit. And in fact, let me change the view here to the grid range. Let's see, view, grid range. And let me keep the x's where they are, but I'm going to go way up, like 1,000. Now look what's happening here. Well, actually, let me zoom way back in here and remind you of something first before we do this. If I zoom in right here real close. Remember that they all go through this point 1, 1, and they reverse direction between 0, 1 than they do above 1. All right, now I'm only going to talk about powers where they're natural number powers. We looked at other powers earlier in power functions, but a polynomial function is just made up of a sum of a bunch of power functions. So if we remember what we know about power functions with natural number powers, we can probably use that to help us understand a lot of things about polynomial functions. Now notice that they go through, the basic ones go through 1, 1 and 0, 0. And between 0 and 1, the bigger power is on the bottom. But when you get to the right of 1, of course they're all the same there at 1. But when you get to the right of 1, the bigger power is bigger. Now I'm going to zoom out again. And I just need to look at the first quadrant. And let's go out to 10. But let's go 10 here. But let's go out 100 here. Okay? We can't really see them all up here. So let's go out much more. Let's go out, let's see, let's go out to 100,000. 5 zeros, yeah, let's try that. Now look what happens. This is x to the 5th, the green one's x to the 4th, the red one's x to the 3rd, the blue one's x to the 2nd power. If you go out here far enough to the right, look how much farther ahead the x to the 5th is above the other. Not only is it ahead of the other, it completely dominates. It's just way ahead. And so if you add this little amount here or subtract it, you're not going to budge this thing too much. It'll certainly change the y value, but it won't change it very much. So if I take x to the 5th and say minus x to the 4th, yeah, it's going to change it some, but it's not going to budge it too far off of what x to the 5th is doing. So that first power is really dominating. And so maybe I subtract even 3x squares from that. Just barely moves it down. Maybe I'll add a 10x to that. And a 7 or something. Very little difference that these things are making. Okay? So they're staying very close to the power of that first power. So it turns out that if you're going to look at the big picture, that first power is the one that dominates. So if I take something like, let's make sure you understand this. Let's take y equals 3x to the 5th. Okay? Now that's a coefficient of positive coefficient, so it's going to look just like x to the 5th. It's pretty much going to be stretched a little bit. But notice on the right, the arrow points up. On the left, the arrow points down. Now, if I take this and say, oh, even a big term like minus 10x to the 4th plus 6x squared minus 2x plus 8. Now, right in here, boy, wow, that looks very different. These things don't look at all alike. But look what happens when I zoom out a bit. Okay, so we're going to come back to the detail in a minute. But what if I go from minus 100 to 100 for y's? Still, you can see quite a bit of difference in the two. But let's go even further out. Minus 10,000 to 10,000. Now what do you see? Well, you see that, in fact, these have a same basic shape, at least here on the end. Now, when we zoomed in here close, maybe they don't look anything at all alike. But on the ends, if you go out far enough, what's happening is that first power, that x to the fifth, is so much bigger than everything else put together that it's basically behaving more or less like 3 times x to the fifth would. And if I go out even further, you're going to see this even more pronounced. So now at this scale, they look very, very much alike. Now they're not exactly alike. There are different numbers there. So they're not, I'm not saying these are exactly the same y values. I'm just saying the basic shape is the same. So in fact, the arrow on the right, once you get sort of past all the ups and downs, it's eventually going to be increasing concave up, just like 3x to the fifth, and about the same rate as 3x to the fifth. And again, after you get past all the little ups and downs in the middle, and you look over on the far left, this polynomial is going to be like the first term, 3x to the fifth, which is increasing concave down here on the last piece. So the arrow points down on the left and up on the right. That's that basic odd thing going on. Now, by the way, don't be confused with even and odd degree and even and odd functions. Even and odd functions have to do with symmetry. Even and odd degree have to do with the power on this. So this is an odd degree function because the biggest power is 5, an odd number, and so it's going to behave a lot like just y equals 3x to the fifth, which is the blue one, I think. Okay? But notice, if we go back to our standard view, this is definitely not either an even or an odd function. It's not symmetric about the y-axis or the origin. So this is clearly not an even or an odd function, but it is an odd degree function. So, how can we, let's summarize a couple of things. Okay, so the leading coefficient determines the direction on the arrow on the far right. If AN is positive, then the right side arrow goes up, and if AN is negative, it's been flipped over and it goes down. So remember our we've got our two basic setups, right? We've got our even power, y equals x squared, where the arrows go the same, and x to the fourth, x to the sixth looks the same, right? More or less, not exactly the same, but kind of. And then you've got your odd pattern, y equals x cubed, y equals x to the fifth. Those look like that. So the odd pattern, the arrows are pointing opposite each other, and the even pattern, they're pointing the same direction on the ends. Okay? Now, look at the right arrow. All of these are pointing up. But if I were to take this and put a negative in front of it, it's going to flip it over the axis, so now the arrow is pointing down on the right. Okay? So that leading coefficient is going to tell you which way the arrow goes on the right. Like negative x to the fourth, that's going to go down on the right. And again, if you add other terms to it, it may change what's happening here in the middle, but eventually, after it sort of finishes, sowing its wild oats, you might say, going up and down, doing whatever it does there, then eventually it's going to settle down, and it's going to behave very much like a power, that leading coefficient term. Okay? So the polynomial function inherits its end behavior from the first term, for the leading term. All right, some terms here. Most of these we've done before, but let's go over them again. A root or zero of a function is an x value which makes the function y value, the second coordinate, 0. So a root, r is a root of p of x if p of r is 0, or a 0 of p of x if p of r is 0. Notice that a root r is a real number. This corresponds to an x-intercept, where the graph crosses the x-axis, or 0. Usually we use the word 0 when we're talking about functions in general, and we talk about roots when we're talking about things like polynomial functions. Okay, so a root of a polynomial, p of x, has multiplicity m if and only if x minus r to the m is a factor of p of x, but that's the biggest factor. You can't put another x minus r in there. Okay, so for example, we've already seen examples of that in if you have a perfect square trinomial, it factors as a binomial square, and that function then has the same root twice. Okay, so in one sense, all polynomials, all quadratics have two roots, but it might be the same one twice, not necessarily two different roots. So a point x comma p of x is a local maximum if there exists a circle, we call it a neighborhood, around the point such that this point has the largest second coordinate of any point which is in the interior of the circle and on the graph of the function. Similarly, a local minimum is the lowest point in the neighborhood. A local extremum is either a local maximum or a minimum. A global maximum has the largest second coordinate of any point on the function. A global minimum has the absolutely lowest second coordinate. Okay? Instead of global maximum, you might say absolute maximum. We use that terminology sometimes as well. And same way for global minimum. That might be an absolute minimum. And you can also talk about, if you use absolute, then you'll probably use the word relative up here. So you'd say relative maximum here, and local minimum, and you could say local would be a relative. Okay, so a relative minimum or a local minimum is the same thing. A local maximum or relative maximum is the same thing there. Okay. If you don't care whether it's a maximum or a minimum, you call it an extremum. Okay. The plural of maximum is maxima. The plural of minimum is minima. Those are Latin. That's the Latin plural. And the plural of extremum is extrema. An inflection point is a point on the graph which the function changed from concave up to concave down or vice versa. So an inflection point or point of inflection. So, we've already said it turns out all linear functions are just transformations of the power function p of x equals x. All quadratics are just transformations of y equals x squared. But if the degree gets 3 or more, there turns out to be more possibilities, and they're not just simply transformations of power functions. So generally, as the degree gets higher, the more possibilities there are for interesting things to happen in the graph. Specifically, the higher the degree, the more you can have roots. The more roots you can have, the more local extrema, the more inflection points that could possibly show up if the coefficients are right. So it may go up and down for a while, but it can only go up and down so much. And eventually the end behavior will settle down to what we've seen earlier. So it's possible to pick a finite region that contains all the interesting parts of the graph, although sometimes it's not possible to pick one window where you can really see all the interesting things. Like, there may be a window where if you're zoomed out far enough to see a minimum, you can't see maybe a local maximum somewhere else. And if you zoom in close enough to see that maximum, you lose the minimum. So recall that if we have a function, well, let's look at it this way here. Suppose I graph, I'm going to put this in factored form. So we'll look at the factored form for just a minute. And let's start with linears. So we'll do the factored form, 3 times x minus 2. Notice that in this form you can clearly see the x-intercept, that it goes through positive 2. So if you say negative 4 times x minus 2, or negative, or 1/2 times x minus 2, notice that that doesn't change where it crosses the x-intercept. Okay, so that coefficient there in the front, in the factored version, changes whether it's been flipped over the axis or not. It changes whether the arrow on the right is up or down. So notice the positive ones had the arrow up on the right, and this last one was a negative, not the last one, but the green one, had an arrow down on the right, and that has a negative coefficient. But it didn't affect where it crosses the x-axis. If I want to do that, for example, I need to change this number like say x minus 6, now it crosses the x-axis at 6, 0. Or if I say x plus 11, now it's going to cross the x-axis at negative 11. Okay. Now, what happens if I put another factor in there? We've seen this already. So let me just do x plus 2 and x minus 3. Well, we can clearly see from the factored version, we've done this before with quadratics, that if x is negative 2 or x is positive 3, it's going to cross the x-axis, so we know it crosses there. Well, polynomials have to be connected and continuous, so it's either going to cross there, and it has to be one connected piece, so somewhere in the middle, actually, and for a quadratic, exactly halfway in the middle, it's going to have a local and global extremum, in this case the lowest point. Now if I put a coefficient in front of this, this is going to stretch it, like if I put 2 there, or put 1.3 there, we get different amounts of stretch. If I make it a negative there, negative 0.8, it's going to be not only stretched a different amount, but flipped over the x-axis. Okay? And so we can see if it's been flipped over. These ones with the negative coefficient have the arrows pointing down on the right. The ones with positive coefficient have the arrow pointing up on the right. But notice the x-intercepts. They're given by these factors. So look what's going to happen if I change this. We'll leave the negative 0.5, but suppose I change this now to say x plus 4 and then x minus 5. Well, now we know that's going to go through 5, 0, and negative 4, 0 on the axis. You can see those places where it crosses the axis. Okay, so what's going to happen, let me go ahead and graph that. What's going to happen if I put another factor in there, say x minus 1? Well, we know it's got to cross the x-axis 3 times. Okay, and let me make something smaller here. Look at that one. We know it crosses the x-axis at negative 4, 0, 1, 0, and 5, 0. So negative 4, 1, and 5 are the roots, or the zeros, and they indicate the x-intercepts. But this one has 3 factors, so it crosses the axis 3 times. Okay? Interesting, huh? Now in between that, in between 2 of the roots, it's got to have a maximum or a minimum. Okay? So this one has a local minimum over here somewhere in the vicinity of negative 2, and over somewhere in the vicinity of 3 or so, 3 point something, it has a local maximum. And in between the max and min, somewhere in between there, it has an inflection point. There it is by itself. Now that leading coefficient is negative, so you see the arrow down on the right. We see if we multiply this all out, we get negative x cubed, and so we know the end behavior is going to be a lot like the negative x cubed, so the arrow is going to be up on the left and down on the right. Now, this is in a factored, we're going to do this in a factored form. So where we have real number factors. So let's do another one here. Suppose we say x. Well, let's take this and put another factor in there. So what if I do x plus 6? Well, we added another root. It's going to cross the x-axis the same places as this brown one here, but it's also going to cross the x-axis at negative 6. Well, that gives us one more root, and that gives us one more change of direction. Let me make this, let me squish it by a factor of 10 more. And so now look at what happens. Notice it crosses the x-axis now at negative 6, negative 4, 1, and 5. Let's get it there by itself. See that? Now it has a coefficient of negative 0.01. Coefficient of negative says on the right side the arrow should be pointing down. even power for the first one. There's four terms here, 4 factors I should say, and you multiply it out. The first term is negative 0.01 x to the fourth. So overall, it's going to look a lot like negative 0.01 x to the fourth on the end behavior. Not so much here in the middle where we are now, but if you can already start to see it a little bit, how this is starting to look similar on those ends. In between the, so that's kind of the end behavior. Let me get rid of that one. So in between these roots, you're going to have extrema. So this one goes up, down, down. So 3 changes of direction, 3 extrema. 2 of them are maximum, 1 a minimum. And they're going to basically alternate between maxes and mins. So you're going to have basically half will be maximum, half will be minimum. Of course, that's an odd number. You'll have one more than the other. But here we go. We have 2 local maxima and 1 local minimum. This one right here is actually a global maximum as well. Well, what's going to happen if we put another factor in there, x minus 3, now look what happened. Well, now it goes through all those same places the other one did, but also over here at 3, 0. Notice this time it was degree 1, 2, 3, 4. It's a degree 5. The first term is negative 0.01 x to the fifth. And we have 5 factors. We have 5 x-intercepts, 5 roots. We have 4 extrema. And we're going to have 3 inflection points. Here's 1, here's 1, here's 1. Alright, so roots correspond to factors. So again, we can just, now that we've seen this, we can sort of describe this without ever having to graph it. So let me just give a rough sketch here of some of these, and you can of course get graphs, better looking graphs, using Graphmatica or your calculator or whatever. But this one I see factor, that says it's going to go through here at negative 2. This is going to says it goes through over here at positive 3. And this says we're up on this end, and it's even power, so we're going to be up on this end. Somewhere in here it's going to min out. And so it looks roughly like that. How about B? Well, I know that over here at negative 2, it's going to cross. Then at positive 3, it's going to cross. And at positive 5, out here, it's going to cross. So it touches the axis those 3 times. And the leading coefficient is 2, so I know on the last piece it's going up. Now we got an odd number here, so it must be going down here this way. So actually, the function itself is going up. The arrow's pointing down. So as you go left to right, it goes up. Somewhere in here, it's going to, I don't know how high, but it's going to max out. It's going to come back down, min out, and go back up. Now that's not a very good looking picture of it, but you are going to have those features that somewhere in here you're going to have a maximum, and here you're going to have a minimum. Somewhere in there. And so I know that is what it's going to look like. Well, erase here a little bit. What about, let's do D. What about D here? Well, 1, 2, 3 factors. We're going to see 3 roots. Negative 2, 8, oops. Eight's out here somewhere. This is not the scale. Negative 4, somewhere over here. And it crosses at those 3 places. The leading coefficient is negative, so the last piece is going down. There's an odd number here, so that means the other end's going the opposite way. So it comes down here, minimums out, back up, comes up here, and it comes back down. Okay? Now, I don't know. This guy may be real close to the axis, and this is going to be way far down there. I don't know. I'd have to check it out. But we could graph it to actually see some more detail. How about this last one, F? Okay, let's see. Negative 2 crosses there. Positive 8. Negative 4. Positive 5. And negative 6. So there are 1, 2, 3, 4, 5 factors. There are 5 roots. The last one is negative, so it's going down this way. Odd number there, so the other opposite arrow here, so it must be coming down. Turns around, a minimum. Comes up, must have a maximum. Come down. Must have a minimum in here somewhere. Comes up, maximum, and come back down. Now the relative size of these pieces, I don't know. We'd have to actually graph it and see. But I do know some of the basic features just by looking at the characteristics that we've seen on the formula. So you should go through here and actually try these. So how do factors relate to x-intercept? Well, every factor relates to an x-intercept. So every time a factor is set equal to 0, that x value will be the x value for an x-intercept. The number of factors, the more factors you have, the more x-intercepts you have, if they're different factors. Now, the number of extrema, assuming if every time you have a couple of roots, then you get an extrema in between. So if you've got n factors, you could have n minus 1 extrema. And between the extrema, you have inflection points, so you're going to have n minus 2 inflection points. Now, this is assuming we didn't have any repeats. So let's take a look and see what happens if we do some repeats. Okay, so let's do, I think this is y equals x minus 1. Now what happens if I do x minus 1 square? Well, look, if you look, it touches the axis and then turns around there. What about x minus 1 cubed? Well, that's your inflection point. What about x minus 1 to the 4th? Okay, so all the even ones, let's try some other ones here, have a certain pattern to them. So let's take let's say x minus 10, and if you have an even power on that, like a square, or a 4th power, or a 6th power, what if you even have, let's do an 8th power, but let's do a negative coefficient. Look what happens. In all these cases, it hits that point and then touches and turns around. So an even multiplicity root, it's going to actually not go through the axis to the other side. It's going to stay on the same side of the axis, except it's just going to touch it right at a local extremum. Okay. Now let's look at what happens here. Let's see if this keeps going. So let's take x minus 2 square. Notice it touches at 2. Well, what if I put another factor on that, x minus 3? Now it's a little harder to see. Let me redo that one. Let's make it spread out. X minus 5. Okay. So look what's happening here. It still touches and turns around there at x minus 2, but then over here at x minus 5, if you zoom in close right here, it looks a lot like a straight line going through there. Whereas if I zoom in close here, it looks a lot like a parabola touching there, or an x squared or x to the 4th, something like that. Okay? Now what happens with the odd power ones? Okay? Well, let's take y equals x minus 5 cubed. Well, we know that that is our inflection point right there. Well, what happens if we put another factor on here, let's say x minus 1? Well, now we still got that. Still, if you look just right in here, it looks a lot like this, the y equals x cubed does there, x minus 5 cubed does there. You've got the inflection point. Okay, when we look back at the bigger picture, we also have something over here, when you zoom in, that looks more or less like a straight line. Okay, what if that made that x minus 1 but made it square? Well, let's clear this out again. Okay. Well, right here, if you zoom in, it looks a lot like that x cubed shape. It's an inflection point. But if you zoom in close over here to this inflection, to this root, x-intercept, it looks like an x square or something, or an x to the fourth, where it touches and turns around. So you've sort of got three different possibilities. Okay, and you can see all three of them on this this green graph. You could have a multiplicity 1 root, and multiplicity 1 roots are called simple roots. If you zoom in on those, they look pretty much like a straight line going through the graph, going through the x-axis. So the graph goes through the x-axis like a straight line. If you got a multiplicity 2 root, then when we zoom in close, it looks a lot like a y equals x square situation where it touches and turns around. But if we have a multiplicity 3 root, or 5, or 7, or 9, any odd multiplicity, well, any odd multiplicity, notice it goes through the axis to the other side, including multiplicity 1 or 3. But if the power is bigger than 1, and it's odd, like power 3, or 5, or 7, then you're going to get an inflection point at the root. If the power is even, like 2, 4, 6, 8, any of those powers, you're going to have a minimum or a maximum at the root. You're definitely going to have a local extremum. And you can experiment with these here to get that on your own. Now, we have some other possibilities. If you have a polynomial here, and you factor it all the way out, but it has some i's in it, then these, if it's going to be real coefficients to start with, these guys have to be conjugates of each other. So this is the complex conjugate theorem that says if you've got a polynomial with real coefficients, then if it has any non-real roots, they have to be conjugates. Remember, conjugates are it says if one of them is a plus bi, the other one's a minus bi. And so if one of these is a root, so is the other one. And so basically, where do these factors come from? They come from a binomial that you can think as, well, it could be a sum of two squares, basically. One example, at least. Okay? And so now we have three factors in linear factors, and we have three roots. So in A, we have three linear factors, three roots, but only one of them is real, and that only the one real one is the one x-intercept. In B, you have four linear factors. Two of them are the same, and two are different. So a total of four roots if you count multiplicities, three different ones. Okay, and of those three, let's say, so four if you count multiplicities. But if we count only different roots, total different roots, there are only three. One is real, and that one is an x-intercept. So these imaginary ones or non-real ones turn out to come in pairs. So these numbers can go down, but only in pairs. The number of real roots can be less, but by pairs. Alright, I've already talked about end behavior here. I've already seen a picture of something like that in this video. So here's a polynomial. It's got a lot of terms. There's several things that we can know about the end behavior, the big picture, and we know a lot about the little picture. The big picture is if you multiply all this out, you get 8x to the fourth, at least. That's easy to do. X times x times x times x times 8. And so on the end, we know it's going to look like 8x to the fourth. It's going to go up on both ends. We also know somewhere in the middle here, it's going to go through -2, -1, 3, and 5. So we know it's going to go down, up, down, up. Okay, so we know a lot about that just without graphing it. So here's the actual picture. Now, close up again, those are fundamentally different. You can see the roots there, -2, -1, 3, and 5. And like I said, down, up, you see 3 extrema, you see 4 roots, and you see 2 inflection points. One's right in here, one's right in this area. Whereas this y equals x to the fourth, or I guess it's 8x to the fourth, it doesn't have any, it just has one minimum here, no inflection points, no other max or min. But as we zoom out, then you see that on the ends, they look pretty similar. There they look fairly similar. If we zoom out even further, definitely that similar kind of shape. So not only is it arrow up on the left and arrow up on the right, it actually the basic shape, the basic rate of growth there is very similar to what it would be for 8x to the fourth. So remember our basic 4 shapes for power functions. See a little bit more. Get back to where I was here. There we are. I think you can see this. So if we have a positive leading coefficient, in both cases, even or odd power, the degree, the highest power, you're going to see the right side go up. If the leading coefficient is negative, the right side is going to go down. For the odd power, the arrows are going to be opposite each other, and the even power, the arrows are going to be the same. When I'm talking about the power, here it's on a power function, but in general, it's going to be on that leading term. Okay? So here, I'll do one of these for you. What power function does this look like? Well, just whatever that first term is, if it's in decreasing order. So that looks like a lot like 2x cubed. So on the ends, here's 2x cubed, looks like this. Well, again, in the middle, here it may not look anything at all like that, but I do know that somewhere down the way, on the ends, it's going to look a lot like the 2x cubed. Arrow up on the right, arrow down on the left. So on this part over here, it's going to be increasing concave down, and over here it's going to be increasing concave up. Now in the middle, who knows? It might have some ups and downs. Okay? So I think that's enough for this video. We'll come back in the next one and continue to talk about more about polynomial functions and their shapes, and we'll look at a lot of different examples in that video.